In the last lecture we had started actually proving the characteristic function or deriving the characteristic function of a Wishart distribution. Let's see where we were actually in the last lecture. So we were looking at proving this particular result that suppose A has got a Wishart distribution m dimensional with degrees of freedom as small n and the associated variance covariance matrix as sigma, then the characteristic function of A, the random matrix, it's a symmetric matrix. So we are looking at the joint characteristic function of m into m plus 1 by 2 distinct elements of A given by denoted by Aij. So this quantity is what is giving us the joint characteristic function or the characteristic function of the Wishart distribution, which we were trying to prove that it is determinant of Im minus I square root of minus 1 times gamma into sigma, determinant of that whole raised to the power minus n by 2, where a gamma matrix was given in this form and sigma matrix was the associated variance covariance matrix. So in proving this particular result, we had come up to this point that we had shown that this characteristic function is of this form, that it is expectation of e to the power I by 2, then summation j equal to 1 to m up to the dimension of the underlying multivariate normal distributions of lambda j v j square and whole these thing raised to the power n, where this lambda j is where the eigenvalues associated with sigma half gamma sigma half matrix. So that this lambda, capital lambda matrix is the diagonal matrix containing the eigenvalues lambda 1, lambda 2, lambda m, and this vj's are independent chi-square random variates because vj squares are independent chi-square random variates. Each of these elements vj's which are there in this vector v has got IID normal with mean 0 and variance equal to 1. So they were standard normal variates, and we realized that this V is V1, V2, Vm, which has multivariate normal, Im with a null vector as its mean vector and Im as its variance covariance matrix. So that would imply these things straight away, and this V1 square, V2 square, Vm square are IID chi-square 1 random variate. And hence, using the characteristic function of a chi-square random variate on 1 degrees of freedom, what we had was this: each of the Vj square random variates had a characteristic function this. So this would imply now that the characteristic function of the Wishart distribution, in which we were interested in, which we had expressed in terms of that expectation, would now take the form that this is I equal to 1 to up to m 1 minus 2 I t, means this t here, when we look at the form of the expression, that's what we had. It's basically lambda j by 2 is serving the purpose of that t in the characteristic function expression, so that this will be a lambda. Let me write this index as a j because we have already used this I for the complex number, and hence this is this lambda j by 2 whole raised to the power minus half, and then this entire expression is raised to the power n. So that inside this bracket what we have is this quantity computed for each of these chi-square random variates, and that raised to the power n. So what is this? This can be written as j equal to 1 to m 1 minus I times lambda j. This I take minus n by 2 outside and keep it here. Now what is this quantity? Note that if we look at this product j equal to 1 to m 1 minus I times lambda j, this can be written in terms of determinant of two diagonal matrices. What are those? This is Im minus I times this capital lambda. So that this resultant matrix here will also be a diagonal matrix with elements as 1 minus I times lambda j. and then the determinant of that diagonal matrix would just be the product of the diagonal entries. So this is equal to this. We can make further simplification to this expression, and this determinant of Im minus I times capital lambda. Now remember that this lambda is that diagonal matrix containing the eigen values lambda 1, lambda 2, lambda m, that is from this expression what we have is this lambda matrix is H sigma to the power half gamma sigma to the power half H transpose. So we can simply take that and write it here, that this is equal to Im minus I times H sigma to the power half, then this gamma matrix sigma to the power half into H transpose. Now pre and post multiplying by determinant of H transpose and post multiplying this expression by determinant of H, we can take H transpose inside, but here we will have that H transpose H, which will once again be an identity matrix, and here if we multiply by H transpose, then this becomes an identity matrix, and if we post multiply this by H, so H transpose H also will become an identity matrix. So what we will be having is I times sigma to the power half gamma sigma to the power half. Now this expression, let me write this expression. This is, suppose we pre-multiply this now by sigma to the power minus half determinant, this multiplied by Im minus I times sigma to the power half gamma sigma to the power half, and then post multiply this by sigma to the power half's determinant. So we can take this sigma to the power half inside this expression and sigma to the power minus half from the left hand side and sigma to the power plus half from the right hand side. So what we will be having is determinant of Im minus, so this will be an identity matrix, this would be I times gamma matrix that multiplied by this sigma matrix, right. So if we have this expression, which is now from here in the final expression of the characteristic function, which we had this term, and we have shown that this term is determinant of this Im minus I times gamma sigma. So this would imply that the characteristic function of A is finally given by the form that was desired, that this is at the point script theta matrix. So this is determinant of Im minus I times gamma into sigma, determinant of that raised to the power minus n by 2. Now if we look back at the statement of this particular result, this is what we were supposed to prove. So phi A script theta was determinant of Im minus I times gamma sigma whole raised to the power minus n by 2, and this precisely we have derived in this particular form. So that's the desired form of this particular characteristic function of the Wishart distribution. So the characteristic function of the Wishart distribution can actually be used to prove many of the results, and it's a fundamental concept, and hence we had looked at the derivation in detail of the characteristic function of the Wishart distribution. Now let me go through some important results in the Wishart distribution theory before we actually move on to defining what is Hoteling's t-squared distribution and how Hoteling's t-squared distribution is obtained from the Wishart distribution and a multivariate normal distribution. Let's first look at this important result. If we have A following a Wishart distribution, Wishart M n sigma with n greater than 0, a positive integer, n is an integer, it's the degrees of freedom, it's naturally an integer, because in the definition of a Wishart distribution we have this n as a number that is associated with the multivariate normal distributions which is associated with that Wishart distribution. So if we express A using the first fundamental definition of the Wishart distribution, we can write A as a summation yi transpose, and that summation is from I equal to 1 to up to n. So the n, the degrees of freedom, is associated with the number of independently and identically distributed multivariate normal distribution, each having a mean, each having a multivariate normal m dimensional with mean vector as a null vector and a covariance matrix as a sigma matrix, and hence this of course is an integer, but for completion I write that as an integer, and y is an m by 1 random vector independently distributed of this random matrix A with this, that probability that y vector takes the null vector is equal to 0. It would be obvious why we take such a condition. Then the distribution of y transpose A y is going to have a central chi-square, well, that result we had noted last time actually, so we will proceed with that result. We will have this written as y transpose A y, this divided by y transpose y transpose sigma y. This will follow a central chi-square on n degrees of freedom and is independent of this random vector y. Now note that first I had written this y transpose A y. The distribution of y transpose A y is obvious actually, because we had proved a result on Wishart distribution which said that if A has a Wishart distribution, then for a constant matrix A we will have A sigma A prime to have a chi-square distribution, to have a Wishart distribution, and if we have certain condition, then that would follow a chi-square distribution. Now this result tells us that if we are looking at this particular ratio, that y transpose A y by y transpose sigma y, that would follow a central chi-square, and that would be independent of this y. Now what we know to start with is the result that I was referring to. We know that if we have A to follow a Wishart m n sigma, then for a constant matrix M, which is say k by m order, we have m a m prime to follow a Wishart distribution k dimensional on n degrees of freedom and with the associated variance covariance matrix as m sigma m prime. We had explicitly proved this particular result that such a result holds true. Now what we will be doing in order to prove the given result is, we will assume first that for a fixed y equal to this small y, so this is for a fixed value of this y equal to y, what is going to be the distribution of this y transpose A y. Now since we are taking y as fixed, it is as if that y is given to be small y. So at that particular fixed point we will have this distribution. The distribution would follow from what we have here in the previous slide, that if we take now m equal to y, then, or rather m equal to y transpose, so this is basically in the previous result we are taking m equal to y transpose. So what we will be having this as Wishart distribution Wishart k. Now what is the order of k here? K is equal to 1 because we are taking y transpose. Y is a vector which is m dimensional. So this is going to be Wishart with degrees of freedom as n, and what is going to be the variance covariance term here? That's going to be this for a given small y, I should write. So let me write that as y transpose sigma y. So this expression for given y will follow a Wishart distribution 1 n y transpose sigma y, because what we have done in the previous result is to just use, or rather take m to be equal to y transpose at this particular given small y value. Now realize the following: what is so special about a Wishart distribution on 1 degrees of freedom? Let me write it as realize that if we have a z following a Wishart distribution on 1 n sigma square. Now since this is 1 Wishart on 1 dimension, this is going to be a scalar quantity. As you can see here, this is y transpose sigma y. So this is 1 by m, this is m by m, and this is m by 1. And hence this y transpose sigma y, that's actually a scalar quantity. So if we have z following Wishart 1 n sigma square, this would imply that z from the definition of the Wishart distribution would be summation I equal to 1 to up to n yi, some other random variable, not to be confused with these yi's here. So from the definition, this is yi transpose. Now what is that about these yi's? This y1, y2, yn, these are scalar random variables. These are going to be IID, normal, one dimensional, because the associated Wishart is one dimensional. This with a mean 0 and a variance equal to sigma square. That is, now it's equivalent. One can actually remove this transpose because these are scalar random variables. So this is nothing but summation I equal to 1 to n yi square, right? So this follows Wishart 1 n times sigma square. But independently, just looking at this particular summation I equal to 1 to n summation yi square, each of these yi's are normal 0 sigma squared and they are independent. So this would imply that this z, which is summation yi square, that divided by sigma square, will follow what? That will follow a chi-squared central on n degrees of freedom, because what we are doing is z divided by sigma square is nothing but summation yi square by sigma square. So each of these terms, yi square by sigma square, they have a chi-square random variate on 1 degrees of freedom. So since they have got chi-square on 1 degrees of freedom, we have the summation of n such independent chi-square random variates to have a chi-square on n degrees of freedom. So we will use this particular thing that if z follows a Wishart 1 n and a scalar sigma square, then this z by sigma square has got a chi-square distribution. So what happens if we use that in this result? So this will imply that for a given y equal to y, this y prime a y, this divided by the corresponding sigma square there, which is y transpose sigma y. I'll just put it like given this y equal to y, this will follow straightforward a chi-square on n degrees of freedom. Now if we have the distribution of this given y equal to y, a chi-square random variate, we note that this distribution that we get of this quantity given y equal to small y is independent of this y. So whatever be the fixed value of this y vector at small y, whatever be the fixing vector here small y, this is always going to have the same identical distribution, which is a chi-square distribution on n degrees of freedom. So this would imply, now this is basically the conditional distribution of this given y equal to y, that's following a chi-square n random variate, and that's independent of the fixing small y of this random vector capital Y. So this would imply that the unconditional distribution of this y transpose AY, this divided by y transpose sigma y, this also is going to have the same conditional distribution. This is the conditional distribution of y transpose AY by y transpose sigma y given y equal to small y. That has got a chi-square distribution, and that does not depend on the particular fixing vector y, and hence the unconditional distribution of y transpose AY by y transpose sigma y is also chi-square random variate. We see that the conditional distribution is the same as that of the unconditional distribution, and hence this basically is independent of this random vector y and is independent of this random vector y. So thus proving this important result that this has got a chi-square central on n degrees of freedom, and this random variable here is independent of this vector y. Let's see how readily we can use this particular result for random sampling in case of a normal distribution. Suppose we have x1, x2, xn, a random sample from a multivariate normal m dimension with a mean vector mu and a covariance matrix sigma. Both mu and sigma are unknown. Sigma is positive definite. Then we have the two quantities of interest, the two statistic x bar, which is 1 upon n summation of these xi quantities, I equal to 1 to n. This is a sample mean random vector, and s, say n minus 1, 1 upon n minus 1 summation I equal to 1 to n xi minus x bar into xi minus x bar transpose. So we have these two quantities of interest, that x bar and Sn minus 1. We have proved in the last lecture and the lecture prior to that the important result that this x bar follows a multivariate normal M with a mean vector mu and a covariance matrix sigma by n, and n minus 1 Sn minus 1, which is this expression, the sum of squares and cross product matrix. This has a Wishart distribution. This has a Wishart distribution M on n minus 1 degrees of freedom and an associated variance covariance matrix of sigma. And furthermore, we had importantly proved that x bar and s are Sn minus 1 here. One can also write this as Sn, so whatever be, they are going to be independent. So this x bar and Sn minus 1 are independent. Right. So we will use these two in order to get to an expression which is very much of interest. We will basically be using the previous result here. Now note that if we have got x bar to follow this multivariate normal distribution, this would imply that probability of x bar vector to be equal to null vector. What is that probability? That probability is equal to 0 because it's a multivariate normal distribution. So that random vector taking this vector null vector is obviously 0. And this x bar and Sn minus 1, Sn minus 1, they are independently distributed. So what can we do? We can write that this would imply by the previous result that x bar transpose, now this has got Wishart distribution there, n minus 1 s n minus 1 inverse x bar that divided by x bar transpose, and then what is required here is sigma inverse. So this sigma inverse, which is associated with the Wishart distribution, remains as a sigma inverse, this into x bar vector. If we are interested in knowing its distribution, then this has got a chi-square central on what would be the degrees of freedom. The degrees of freedom would be associated with the degrees of freedom of this n minus 1 Sn minus 1 Wishart quantity. So that's a chi-square on n minus 1 degrees of freedom and is independently distributed of the random vector that is x, right. So this quantity, this one can simplify this and write this as n minus 1, so that this would be oh, there is no inverse there. So by the previous result, this of course the next result is going to involve the inverses. So this is going to be just x bar transpose n minus 1 s n minus 1. That is going to have a chi-square distribution, because let me just go back one slide, so that this is what we have is y transpose the Wishart matrix here y. So that would be having this chi-square distribution, and hence this distribution here, this x bar transpose s n minus 1 into x bar, this divided by there is no inverse here, the inverse will come in the next result. So this x bar transpose Sn minus 1 n minus 1 into Sn minus 1 x bar, that divided by x bar transpose sigma times x bar, so that this sigma times x bar, this will follow a central chi-square on n minus 1 degrees of freedom. Now the next that we are going to look at is Wishart partitioning. Partitions associated with Wishart distribution. Now let us make the following partition in the Wishart distribution, which we write as following. Suppose we have A to follow a Wishart distribution M n sigma, sigma of course associated to be positive definite. Now partition A and sigma as follows. Partition A and sigma as, suppose we have A to be partitioned as A11, A12. Now this A11, let us make that a k by k matrix, and this is A22, this is A21 matrix. Now this has now got the order that it is m minus k by m minus k. Now the order of this A12 and A21 are accordingly obtained. For example, A12 has got k rows and it has got m minus k columns, and similarly this has got m minus k rows and k columns, right. So this is a partitioning of A that we have obtained, and rather we have made. We have a similar partition in the sigma matrix, which is sigma 11. This is sigma 12. Let me put this partitioning like this, so that we have this as sigma 21, that into and that sigma 2 component. So the partitioning of sigma is as in the partitioning of A, that is, this is now a k by k matrix, and this sigma 2 is an m by k into m by k matrix. Then we may be interested in knowing what is the distribution of this subpartition here, A11 or A22, or some derived form which involves all the partitioning element of the Wishart matrix. Let me write the results for this setup. Now the first result, that's what we will be having, is A11 will also be having a Wishart distribution, k dimensional. Now remember that the type of partitioning that we had made, A11 is a k by k random matrix derived from the Wishart matrix. So this is a Wishart distribution k on degrees of freedom as the degrees of freedom of the original Wishart distribution, and the associated variance covariance matrix as sigma 1. Now how do we prove that? It's easy actually, all these results can be proved. Now suppose I take an IK matrix augmented with a null matrix, so as to have this as k by m matrix here, that A into the transpose of this matrix. So treating this as the matrix of constant, which is m, A m transpose. So this will follow a Wishart distribution on k dimensions, degrees of freedom remaining n, and the associated variance covariance matrix as m sigma m prime. So this would be m sigma m prime. Now what is this going to be equal to? For sigma, the type of partitioning sigma 11, sigma 12, sigma 21, sigma 22, what we have, this is going to just be equal to sigma 11. So that this partition, A11 partition derived from the original Wishart matrix, will be having a Wishart distribution, Wishart k n sigma 11. Similarly, one also will be having A22, the partitioning, the second block partitioning, that would be having a Wishart distribution on m minus k dimensions with n as the degrees of freedom, and sigma 22 as the associated variance covariance matrix. This can also be proved. Let me write the third result, which is for the Wishart partitioning. We also have the third result as if we look at this A12 given A22, this will be having a matrix normal distribution. This will follow a matrix normal distribution n with the following parameters: sigma 12, sigma 22 inverse A22 as the mean matrix, and the associated variance covariance matrix would be given by sigma 11 dot 2 Kronecker product A22, where this sigma 11 dot 2 is the usual sigma 11 dot 2 matrix, that is, it is sigma 11, sigma 12, sigma 22 inverse multiplied by sigma 21. So the conditional distribution of A12, that partitioning of the Wishart, given A22, this now follows a matrix normal distribution. Note that this is a rectangular matrix, so no question of having this conditional distribution to be having a Wishart distribution, because Wishart distribution is associated with a symmetric matrix. And the third, or rather the fourth and the last result concerning the partitioning of the Wishart distribution is the following. If we define A11.2 as in the similar way as sigma 11.2, which is A11 minus A12, A22 inverse A21, this now will follow a Wishart distribution. The order would be same as A11 or the order of this, so that's K. So this would follow a Wishart distribution K on degrees of freedom as n minus m plus k, and the associated variance covariance matrix as sigma 1 1.2, and is independently distributed of A11 and A22. So these are some fundamental results concerning partitioning of the Wishart distribution. Now the next important concept that we are going to introduce is an inverted Wishart, what we call as by an inverted Wishart. The definition of inverted Wishart is simple and would eventually lead us to Hoteling's t-squared distribution. So if we have A to follow a Wishart distribution Wishart m n sigma, then the inverse of this matrix, inverse of this random matrix, that is A inverse, is said to follow an inverted Wishart distribution. This inverted Wishart actually would also lead us to an unbiased estimator of sigma inverse, which we are going to see shortly. Now an important property of inverted Wishart is the following. Inverted Wishart is the following, that, let me write it completely. Suppose A follows a Wishart m n sigma, sigma is positive definite, m is say k by m, matrix of constants, matrix of constants, and rank of m is full. So suppose we have this particular setup, then for, of course, n greater than m minus k, we will have the following distribution, that m A inverse, m transpose, whole inverse. This would follow a Wishart distribution K on n minus m plus k, and the associated variance covariance matrix as m sigma inverse m transpose whole inverse. So what is this result basically telling us? That if we have A to have a Wishart distribution, and if we have m a matrix of constants k by m order of rank k, that is, it is a full row rank, and for n greater than n m minus k, that's what is required in order to ensure that the degrees of freedom of this Wishart distribution, this is basically n minus m minus k, so we ensure that this is greater than 0, so we have the degrees of freedom strictly greater than 0. Then we have this m A transpose m inverse, whole inverse, will be having a Wishart distribution n minus m plus k, and the associated variance covariance matrix as m sigma inverse m transpose whole inverse. Now using this result of this Wishart distribution, we have the following important result. Suppose we have got A to be Wishart m n sigma, n is greater than 0, positive integer, which we take n to be greater than m minus 1, and sigma, of course, is positive definite, and y is a random vector. Y is a random vector such that probability y equal to a null vector is 0. Then we will have this y transpose sigma inverse y, this divided by y transpose A inverse y. This will now be having a chi-square distribution central on n minus m minus 1 degrees of freedom and is independent of this y vector, right. So this reminds us of a similar result that we had proved today, which actually was without the inverse. It was y transpose A y by y transpose sigma y. It was shown to have a chi-square central distribution on n degrees of freedom. Now, instead of working with the Wishart distribution, if we are now working with an inverted Wishart distribution, then this is basically the result which tallies with the result that we had previously obtained. So this result is simple actually. It basically uses this fundamental result concerning an inverted Wishart distribution, which we said to have an important property of an inverted Wishart distribution. So the proof of this goes along the same line as the proof of the result for the Wishart distribution. So for a given y, if we take this m in this result as y transpose, then what we will be having that this y transpose sigma y transpose A inverse y, it's basically we are using this particular result which with m equal to y transpose. So this for a given y equal to say small y, the distribution of the inverse of this quantity will follow a Wishart distribution with what dimensionality? Now K is the dimensionality associated with the M matrix. Now Y transpose is taking its place, and hence we will have this, the dimensionality of the Wishart distribution to be equal to 1, and what is going to be the degrees of freedom? It's going to be n minus m minus k, so that is n minus m plus k, so that this is n minus m plus 1. So that's the degrees of freedom of the Wishart distribution, and what's the associated variance term? That's going to be equal to y transpose sigma inverse y, then this is whole inverse. So this result is used in order to get to this particular form here. So that what we now have, now we have already seen that what happens to a Wishart distribution on 1 degrees of freedom. So this would imply that this y transpose A inverse y, inverse of this, that was having the Wishart distribution on 1 degrees of freedom, this divided by the associated variance, which is y transpose sigma inverse y whole inverse, this for a given y equal to small y, this would follow what? A chi-square distribution on n minus m plus 1 degrees of freedom. Why? Because of the simple fact that we have got this, the distribution of this given y equal to y has got a Wishart distribution n minus m plus 1, and this as the associated variance term, and hence if we divide this term here by the corresponding variance, we are going to have a chi-square random variate on the degrees of freedom associated with the degrees of freedom of the Wishart distribution. Now this thus is the conditional, this chi-square n minus m plus 1 is thus the conditional distribution of this random variable here, y transpose A inverse y inverse divided by y transpose sigma inverse y. This is basically having a conditional distribution conditioned by y equal to small y is having this. Now this distribution is what we observe is independent of this conditioning variable y, because whatever be the capital Y being fixed at small y, the distribution is going to be a chi-square central on n minus m plus 1 degrees of freedom. Thus, the conditional distribution of this expression given y equal to y would be same as that of the unconditional distribution. So, this would imply that this y transpose A inverse y, this inverse that divided by our y transpose sigma inverse y, this is the unconditional distribution, this is going to also have a chi-square on n minus m plus 1 degrees of freedom, and this is going to be the distribution of this random variable, since it is having the unconditional distribution same as that of the conditional distribution, and this thus would be independent of this conditioning variable, conditioning random vector which is y, and is independent of this conditioning random vector which is y. That is, this is just the inverse of that, so that we have this y transpose sigma inverse y, this divided by this y transpose A inverse y, this to have a chi-square n minus m plus 1 and is independent of this y vector, and that was actually the result which we tried to prove, that sigma inverse y transpose sigma inverse y divided by y transpose A inverse y, this has got this desired distribution. Now we look at an unbiased estimator of sigma squared that is associated with an inverted Wishart distribution. Let me look at an unbiased estimator. These are basically all associated with an inverted Wishart distribution, and what we will be seeing is that inverted Wishart also is going to be used in order to derive to the Hoteling's t-square distribution, unbiased estimator of this sigma inverse. Now, in order to derive this unbiased estimator of sigma inverse, suppose we have got a Wishart distribution. Suppose A has got a Wishart distribution, Wishart m n sigma, then for any fixed vector alpha belonging to R to the power m, of course we take this alpha vector to be not equal to a null vector. For this fixed alpha vector, what we can write is the following, that alpha prime sigma inverse alpha, this divided by alpha prime A inverse alpha. What is going to be the distribution of this? By the previous result, that's what we have proved. If we take alpha to be equal to y in the previous result, with alpha degenerate at a particular point, with alpha not equal to 0, ensuring that this is not equal to 0, so that this will have a central chi-square on n minus m plus 1 degrees of freedom. That's by the previous result, with y degenerate at this alpha point, with alpha not equal to a null vector, satisfying the conditions of the previous result. Now, this would imply that if we now look at expectation of alpha prime A inverse alpha, now this what we are doing for a general Wishart distribution, we will use that in order to get to this unbiased estimator of sigma inverse. Expectation of alpha prime A inverse alpha, let me write that in the following way, that this is alpha prime sigma inverse alpha, that multiplied by alpha prime A inverse alpha, that divided by alpha prime sigma inverse alpha. Note that this part, the first part is constant, so that we will have this written as alpha prime sigma inverse alpha, that multiplied by expectation of this alpha prime A inverse alpha, that divided by alpha prime sigma inverse alpha, right? Now, what is this quantity equal to? So that we can just write that this expression is equal to alpha prime sigma inverse alpha, and then expectation of 1 upon alpha prime sigma inverse alpha, that divided by alpha prime A inverse alpha. Why have we written in this particular form? Because we know that this has got a chi-square distribution. So let me just write this simply as alpha prime sigma inverse alpha into expectation of 1 upon y, say, where this y follows a chi-square distribution on n minus m plus 1 degrees of freedom. Now if y has got a chi-square on n minus m plus 1 degrees of freedom, we know that expectation of 1 upon y would be 1 upon degrees of freedom minus 2. So that this expression straight away we write it using univariate distribution theory, that this is going to be equal to 1 upon the degrees of freedom of this, that is n minus m plus 1, this minus 2. Why is this true? If y follows a chi-square on n degrees of freedom, then expectation of 1 upon y is 1 upon n minus 2. So that we have this as 1 upon n minus m minus 1 into alpha prime sigma inverse of alpha. So that our expectation of alpha prime A inverse alpha is equal to this term. Now this is true for every alpha, every fixed alpha. For every fixed alpha belonging to R to the power m, alpha of course is not equal to this null vector. Otherwise there will be problem in defining this particular random variable here. Now let me use this particular term, that's what we have. Now if we take some special choices of this alpha vector, we will have the desired result. Take this alpha vector to be 0 at all the positions except the ith position. So if we take this as 1 and at all other locations if we have 0, then what is this expectation of alpha prime A inverse alpha? This we know is equal to n minus m minus 1 into expectation of, this is expectation we have already computed, this is alpha prime sigma inverse alpha. So with this alpha in this result, we will have here expectation of A upper II, say, where A upper II is the ith element of this A inverse matrix. That would be given by this alpha prime sigma inverse alpha would be sigma II. Sigma upper II is the ith element of this sigma inverse matrix, that divided by n minus m minus 1. This is going to be true for every I. So we have obtained that expectation of A upper II is equal to sigma II by this. Now further take alpha equal to another choice, taking alpha to be a vector which is having 0 at all the positions except the ith and the jth position. So if this is the ith position and this, say, is the jth position and 0 at all other positions, once again using this particular result, what the alpha prime A inverse alpha would lead us to, this would imply that expectation of A upper II plus 2 times A upper ij, this plus A upper jj. So these are all the elements corresponding to A inverse matrix. This would be equal to, from the right hand side, alpha prime sigma inverse alpha is going to be sigma upper II, this plus 2 times sigma upper ij, this plus sigma upper jj, that is coming from alpha prime sigma inverse alpha, and this is n minus m minus 1. Now we already have a expectation of each of these aii to be equal to sigma ii by n minus m minus 1, and hence this can be replaced by expectation of aii by n minus into n minus 1. So this would further imply, that expectation of A upper ij that would be given by sigma upper ij that divided by n minus m minus 1. So what have we proved? Now this is going to be true for every I and j, so that this is the off diagonal entries, these are the diagonal entries. This is true for every I equal to 1 to up to m, and we have this for every ij equal to 1 to up to m. So this would imply that expectation of A inverse, so every element has got its entries there, so expectation of A inverse would be given by sigma inverse by n minus m minus 1. So we will, in the next lecture, we will use this particular result in order to get to an unbiased estimator of sigma inverse when we have a random sampling from a multivariate normal distribution from this particular result. Thank you.